Welcome back, everyone. Ready for another deep dive?
I'm ready.
Excellent. Today we're tackling the physics of motion. Buckle up, because we're going to cover everything from like how you walk to how planets orbit stars.
It's incredible how motion is literally everywhere. Like we see it on the streets, we feel it in the air we breathe, even the earth spinning beneath our feet, it's all motion.
Wow, I actually never really thought about it that way.
But I guess like when we see something move, it's usually because it's like changing position over time, right? Like a car driving down a road
Exactly.
or a ball flying through the air.
Absolutely. But here's the thing. Sometimes we can't directly see the motion.
Really?
Yeah, but we can tell it's happening because of its effects. Like, imagine wind moving leaves. We can't see the wind itself,
Right.
but we know it's there because it's making the leaves rustle.
That's a really good point. It's like we're like motion detectives.
We find the clues to figure out how things are moving around us. So where do we even start with trying to understand this whole concept of motion?
Well, a good place to start is by remembering that motion is relative.
Relative.
Yeah. It depends on your perspective, your point of view, or as physicists like to call it, your frame of reference.
Frame of reference.
Yep. Imagine you're on a train.
Okay.
You look out the window and you see the trees rushing by. It looks like they're moving backwards, right?
Yeah.
But to someone standing still on the platform, it's the train that's moving forward.
So how we perceive motion depends on where we are and how we're moving ourselves.
Exactly. It's all about comparison. There's no such thing as absolute motion. It's always relative to something else.
I see. So it's like all about relationships.
Yeah.
So to really grasp this idea of relative motion, we need to delve into these concepts of distance and displacement.
Okay.
And I have a feeling those terms might be more complicated than they seem.
You're right. People often use them interchangeably, but in physics, they have very specific meanings. Oh, okay.
Yeah. So distance is like the total length of the path an object takes. Think of it as like how much ground it's covered.
So if I walk 10 meters forward and then 5 meters backward, I've covered a total distance of 15 meters, right?
Exactly. Now, displacement is different. It's the shortest distance between where you started and where you ended up. And it's always measured in a straight line.
So in that walking example, my displacement would be 5 meters.
Precisely. Because that's the straight line distance from your starting point to your ending point.
So you're saying like displacement has to include the direction too. Right?
You got it. Displacement always includes direction. And that makes it a really powerful tool in physics.
Oh, I see. So it's not just about how far you went.
Right.
It's also about like where you ended up relative to where you started.
Exactly. So can you think of a situation where you could travel a long distance, but your displacement would be zero?
Oh. What about a runner going around a track?
Perfect example. They might run like 400 meters, but if they end up back at the starting line.
Their displacement is zero. They haven't changed their position relative to where they started.
Okay, so distance is like the whole journey.
Yep.
And displacement is just like the straight line from start to finish with direction included.
Got it. So we got those basics down. Now, how do we describe how something is moving? Like, is it moving at a steady pace or is it speeding up and slowing down?
That's where uniform motion and non-uniform motion come in.
Okay.
Uniform motion is the simplest type of motion. It means an object is moving at a constant speed and in a straight line, covering equal distances in equal time intervals.
So basically like cruise control on a highway.
Precisely. That's a great example of uniform motion. The car's speed is constant.
Yep.
And its direction is staying the same, so we say its velocity is constant.
Got it.
Now, non-uniform motion is when the speed or direction changes, or both.
So more like driving in rush hour traffic.
Lots of stopping and starting, speeding up, slowing down, maybe even changing lanes.
You got it. Non-uniform motion is much more common in real life.
Okay, I think I'm starting to see the difference.
Yeah.
So cruise control is uniform motion, and stop-and-go traffic is non-uniform motion.
Now I have a question, and it might sound a little silly, but I always use the word speed and velocity interchangeably. Are they really that different in physics?
They are.
Yeah.
Yeah. It's subtle, but important. Speed just tells us how fast something is going, regardless of direction. It's just the rate at which an object covers distance.
Okay.
But velocity is more specific. It's speed plus direction.
Oh, okay. So if I say a car is going 60 miles per hour, that's its speed.
Yep.
But if I say it's going 60 miles per hour east, that's its velocity.
Exactly. Because you've included the direction.
Okay.
Think of it this way. Imagine a race car zooming around a circular track.
Okay.
Its speed might stay the same the whole time, But its velocity is constantly changing because its direction is constantly changing. Ah, I see the difference now. So speed is just like a number,
Right.
and
That-
velocity is that number, but with the direction attached to it. Makes sense. But how do we actually calculate those things?
Well, to get the average speed, you just divide the total distance traveled by the total time it took. So if you drove 100 kilometers in 2 hours, your average speed was 50 kilometers per hour.
Okay, so average speed is like a big picture view of how fast something was moving overall.
Precisely. It doesn't tell you about the details of speeding up or slowing down along the way.
Right.
But average velocity is a bit different. It focuses on the overall change in position over time, taking into account both the distance and the direction.
So it's based on displacement instead of just distance.
Exactly. It gives you a more complete picture of the overall motion, considering both how far the object moved and in what direction.
Okay, I think I'm starting to get the hang of speed and velocity. But what about acceleration? I always think of acceleration as like hitting the gas pedal and speeding up.
That's a common way to think about it, but it's just one aspect of acceleration. In physics, acceleration refers to any change in velocity over time. So it's not just about speeding up.
Wait, so it could mean slowing down too?
Exactly. Slowing down is just acceleration in the opposite direction. We often call it deceleration.
Oh, right.
And remember, velocity includes both speed and direction. So even if you're going at a constant speed, but you're changing direction, you're still accelerating.
Oh, like when you're going around a curve, even if you don't change your speed on the speedometer?
Exactly.
That makes sense. That's why it feels like you're being pushed to the side when you take a sharp turn in a car. It's that change in direction.
Precisely. Acceleration is a vector quantity, which means it has both magnitude and direction, just like velocity. And its standard unit is meters per second squared.
Meters per second squared.
Yeah, it's written as MSS. And it basically tells you how much the velocity changes each second.
Okay, so to recap, we've got distance, which is the total path length. Displacement, which is straight line distance and direction from start to end. Speed, which is how fast something is moving. Velocity, which is speed and direction. And acceleration, which is any change in velocity over time. Did I get all that right?
You nailed it. Now, ready to shift gears a bit and talk about how we can actually see motion in action.
You mean like literally see it?
Well, not always literally, but we can use graphs to represent motion and see the relationships between different variables.
Oh, graphs.
Yeah.
I'm not the biggest fan of graphs, but I'm willing to give it a shot.
Graphs can be a little intimidating, but they're incredibly powerful tools. They can show us patterns and trends that might not be obvious just by looking at numbers.
Okay, so what kind of graphs are we talking about here?
The two most common ones for representing motion are distance time graphs and velocity time graphs.
Distance time graphs, velocity time graphs.
Really?
Okay.
Yeah. So in a distance time graph, we put time on the horizontal axis, which is the x-axis.
Okay.
And we put distance on the vertical axis, the y-axis.
Okay, so what does it mean if we see a straight line on a distance time graph?
A straight line on a distance time graph means the object is moving at a constant speed. In other words, it's experiencing uniform motion.
Okay. And what about the slope of the line?
The steeper the slope, the faster the object is moving.
So a really steep line means really fast motion.
Exactly. Now, what do you think a curved line on a distance time graph means?
A curved line. Well, if a straight line means constant speed, maybe a curved line means the speed is changing.
You got it. A curved line indicates non-uniform motion. It means the object is either speeding up or slowing down.
Okay, so distance time graphs show us how speed changes over time. What about velocity time graphs? Are they similar?
They are similar, but instead of plotting distance on the y-axis, we plot velocity.
Okay, so time is still on the x-axis.
Yes, time is always on the x-axis. So on a velocity time graph, a horizontal line means the velocity is
So
constant.
that means no acceleration, right?
Exactly. And the sloping line indicates acceleration. If the line slopes upwards, that means the object is speeding up.
Positive acceleration.
Right. And if the line slopes downwards, it means the object is slowing down or decelerating.
Negative acceleration. Got it. Is there anything else these graphs can tell us?
Actually, there is. The area under a velocity time graph represents the distance traveled by the object. It's a really neat visual way to see the connection between velocity, time, and distance.
Wow. That is pretty cool. So much information packed into these graphs. Now, I know physicists use equations to describe motion too, but I've always found those a bit intimidating. Can we talk about those in a way that makes sense, even for someone who's not a math whiz?
Absolutely. Equations can seem scary, but they're really just shorthand ways to express the relationships between different quantities. And when it comes to motion, there are three fundamental equations that are super helpful for describing objects moving with uniform acceleration.
Okay, I'm willing to give them a try. But can you give me an example of how these equations actually work in the real world? Something I can picture in my head.
Sure. Let's imagine a car accelerating from a stop sign. Its initial velocity is 0, and let's say it can accelerate at a constant rate of, I don't know, 2 meters per second squared. We can use one of these equations to figure out how fast it'll be going after, say, 5 seconds.
Oh, okay. So we know the starting speed, the acceleration, and the time.
Yep. And we want to find the final speed. That's exactly what these equations let us do. They help us predict how objects will move.
That's pretty amazing. So these equations are like a secret code for unlocking the mysteries of motion.
You could say that. They provide a really powerful framework for describing and understanding how things move. Now, we've talked about uniform motion, where velocity is constant, and non-uniform motion, where velocity changes. But what about when something is moving in a circle? How does that fit in?
That's what I was wondering, too. We talked about how changing direction is a form of acceleration. But how do we describe motion that's constantly changing direction? Like a planet orbiting a star or a car going around a curve. It's like mind-blowing, right?
Yeah.
How something can be moving at a constant speed, but still be accelerating because its direction is always changing. I think we touched on this earlier. You called it uniform circular motion.
Exactly. Uniform circular motion is all about an object moving in a circle at a steady speed. The key here is that the speed stays the same,
Right.
but the direction is constantly changing, which means there's always an acceleration.
Okay, I think I get that. But can we, break that down a bit more? What's actually causing that change in direction?
Well, that's where the concept of centripetal force comes in. Centripetal force is any force that pulls an object towards the center of the circle, keeping it on that curved path.
So it's like there's an invisible string pulling the object inward, stopping it from just flying off in a straight line.
That's a great analogy. Think of a ball tied to a string being swung around in a circle. The tension in the string, that's the centripetal force. It's always pulling the ball towards the center. If that string were to break, the ball would just fly off in a straight line.
Whoa, okay, yeah, I see that. So centripetal force is what keeps things moving in those circles?
Right.
And what's the connection between this centripetal force and acceleration?
The acceleration caused by centripetal force is called centripetal acceleration. And remember, acceleration is any change in velocity. So since the direction of velocity is always changing in circular motion, there's always an acceleration.
Okay, I think I'm following. So centripetal force causes centripetal acceleration, which makes the object keep moving in a circle. It's like a physics chain reaction.
Exactly. And the amount of centripetal acceleration needed depends on two things.
Two things.
Yeah, the object speed and the size of the circle, the radius.
Okay.
So the faster the object is moving or the smaller the circle, the more centripetal acceleration is needed to keep it moving in that circle.
Got it. So we've talked about a lot in this deep dive, like the definitions of distance, speed, velocity, and acceleration. We covered uniform motion, non-uniform motion, and then this whole thing about circular motion. And we even looked at how graphs can help us see all these concepts in action. Now, can we go back to those three fundamental equations you mentioned earlier? I'm still a little bit intimidated by them, to be honest.
Of course, it's totally understandable to feel that way about equations, but they're incredibly powerful tools for understanding and predicting how objects move. And once you break them down, they're not as complicated as they might seem at first.
Okay, I'm ready to give it another try. Can you remind me what those equations are?
Sure thing. The first equation is v equal plus at.
Okay, v equals u plus at.
It tells us that the final velocity, which we represent with v, is equal to the initial velocity, u, plus the product of the acceleration, a, and the time, t.
So if we know the starting speed, the acceleration, and how long the object is accelerating, we can calculate the final speed.
Precisely. Let's say a cyclist starts from rest, which means their initial velocity is 0.
Okay.
And they accelerate at a constant rate of, let's say, 2 meters per second squared for 5 seconds. Using that equation, we can find their final velocity after those 5 seconds.
Oh, cool. So we just plug those numbers into the equation.
Yeah. It would be v equals 0 plus 2 meters 7/5, which gives us a final velocity of 10 meters per second. So after 5 seconds of accelerating, the cyclist is moving at 10 meters per second.
Wow, that's really neat. It's like magic, but it's physics.
Haha, exactly. It's the beauty of physics. Now, the second equation is s plus text.
Okay, S blood plus half stat. What does that one tell us?
This one is all about the distance traveled. S represents the distance, and the equation tells us that it depends on the initial velocity u, the time t, and the acceleration a.
So it's like a way to figure out how far something will travel if we know how fast it starts, how long it's moving, and how it's accelerating.
Exactly. Imagine a ball rolling down a hill. Let's say it starts with an initial velocity of 1 meter per second and accelerates at half a meter per second squared.
Okay.
We can use this equation to figure out how far it'll roll in, let's say, 4 seconds.
So we plug those numbers into SPOL plus IKLOs.
Right. We would get SCLL 1 meters, 4s, plus half my 0.5 meter teeters, which gives us a distance of 8 meters.
Okay, that makes sense. So this equation shows how the distance, initial speed, acceleration, and time are all connected. Now, what about that third equation? You mentioned it's useful when we don't know the time.
Right. The third equation is 2a's is self's VAOL.
Okay, 2a's equals VAOL. So this one is for when we don't know how long the object is moving for.
Exactly. It relates the distance s to the initial velocity u, the final velocity v, and the acceleration a without needing to know the time.
So if we know the starting speed, the ending speed, and the acceleration, we can use this equation to figure out the distance.
Precisely. Let's say a car is accelerating from 20 meters per second to 30 meters per second, and its acceleration is 2 meters per second squared. We can find the distance over which this acceleration happens by plugging those numbers into the equation. 2 meters says in Sutter equals 30 meters, 20 meters of Sutter. And if we solve for s, we find the distance is 125 meters.
Wow. It's really amazing how these equations can tell us so much about how objects move. It's like having a secret decoder ring for the universe.
It really is. It's amazing how much we can understand about the world around us just by using these basic principles of physics.
Well, I think this deep dive has been incredible. We've covered so much ground, from the basics all the way to circular motion and those mind-blowing equations. I feel like I have a whole new appreciation for how things move.
It's been a pleasure exploring these ideas with you. And remember, physics is happening all around us all the time. So keep your eyes open, keep asking questions, and keep exploring.
That's great advice. And until next time, keep those brains buzzing, deep divers.